Okay, so let's go ahead and begin the 9.7 notes or the ocean acidification notes. So here's your learning objective. Explain the causes and effects of ocean acidification. And there were several different essential pieces of knowledge that you need to know that go along with that. So make sure you look at that chart. But essentially, increased CO2 in the atmosphere causes increased ocean, like the dissolved CO2 that we find in the ocean water. This is a direct exchange that just happens like in a cycle over and over again. So CO2 moves into the atmosphere. The more that's there, the more that's available then to diffuse into ocean water. And then it'll diffuse out of ocean water back into the atmosphere. And that's just a cycle that happens over and over and over again. And when the CO2 combines with ocean water, it actually forms carbonic acid, H2CO3. You do not need to know the chemical formula for carbonic acid, but you do need to know that this is a very common theme. We discussed this in Unit 7, and we're now discussing it again in Unit 9, that when CO2 or when NO2 or when SO2 combine with water, it forms either carbonic acid, sulfuric acid, or nitric acid. And we saw what sulfuric and nitric acid did in terms of being in the atmosphere and what impacts it had on terrestrial ecosystems. And so now a major problem with increased amounts of CO2 is that carbonic acid actually impacts um, ocean ecosystems. So that's a real problem, not just ocean ecosystems, but aquatic ecosystems in general. And so what? There's, carbonic acid in the ocean. Why do we have to worry about that? Well, essentially, carbonic acid dissociates into one bicarbonate ion and a hydrogen ion. And so that's not that big of a deal. And I'm going to turn off my camera here. Although it actually is. What it ends up causing is it takes away the carbonate ions so that they're not available to go into marine organisms like coral, different crustaceans that use those carbonate ions, and different zooplankton and phytoplankton, mostly zooplankton. So any marine calcifier that needs calcium to make a shell is now going to be impacted, or to make an exoskeleton, or to make, its um, shells, I guess, in general, are going to now be fewer and smaller. All right. And so that is a real problem that definitely impacts the food web, because those organisms tend to also be on lower levels of the food web. So now they're not able to make their calcium carbonate shells, and so they can't go through the process of calcification, because now there's less carbonate ions available for them. And we've seen a major reduction in the amount of carbonate ions over time. We can see here the pH. Because this carbonic acid is going into the ocean water, it's going to drop our pH. And we can see that seawater's pH used to be alkaline. It was just over 8, in the low 8.1 range, 8.2 range. Now we're seeing that that is actually dropping down below 8. So we're in the high 7 range, which again can really throw some organisms outside of their range of tolerance. If they prefer more alkaline water, now they have closer to neutral water, which can be a real problem. So that is then um, meaning that we're going to have less calcification that can then happen. And if you know anything about the shells of all of these marine ecosystems, or of these marine organisms that are in these marine ecosystems, those shells are made out of calcium carbonate. So they really rely on that mineral being in the water. It's not there. We're now going to get weaker shells, or they're going to be smaller shells. And that's just a problem for those organisms that are lower on the food chain. So here is the shell deterioration when we drop down or put a shell into a solution with a pH of 7.8. Over 0 days, 15 days, now 30 days, now here at 45 days, it just becomes thinner and thinner and thinner, weaker, weaker. And then, if it gets to the point where those organisms don't even survive, that's going to be a real problem, and can cause a collapse of an ecosystem. So, climate change and ocean acidification, what do those have in common? Well, there are anthropogenic causes for ocean acidification. Those are things that we've talked about before. So, fossil fuel combustion releases a bunch of CO2, deforestation releases a bunch of CO2, burning coal and gas produces not just a bunch of CO2, but also a bunch of NOx, a bunch of SOx. And so the increase in CO2 especially is correlated with that ocean acidification. There's an inverse relationship between the amount of atmospheric CO2 and ocean pH. So as the amount of atmospheric CO2 increases, the pH of the ocean water actually decreases, or you could say there's a direct relationship with the acidity of acid water where it's becoming more and more acidic. But with pH, we just say that it's an inverse relationship. The pH becomes lower, which in turn is more acidic. So here's what the graph would look like if we were going to look at a graph of that. And again, I've already mentioned that the pH has decreased in the past 150 years. It's estimated that by 2100, we could see a pH of around 7.8. And don't forget that while it just seems like a small increment on the pH scale, I think it's important to note here that the pH scale is actually a logarithmic scale. So it's exponentially different when we're talking about those numbers. So going just from 8.2 to 8.1 is a 30% decrease, not just a zero point 0.1 difference. That zero point 0.1 difference is a significant decrease. So here is your practice FRQ for 9.7. Identify one human activity that leads to ocean acidification and explain how ocean acidification can threaten marine organisms. All right, our next section is going to be on 9.8, and in that section, we're going to be covering invasive species. So that's it for 9.7. I'll see you guys next time.